Fine. So yesterday we've seen, I deduced the hydrodynamic behavior of independent random walks. So now I'll go back to the model we introduced 2 or 3 days ago, which is the exclusion process. So this symmetric exclusion process. And I want to do exactly the same thing. So I want to start with some initial profile rho and to deduce the, so let's say that we are time t. So since if we follow just a particle and we wait for this particle to move, it might move to the right or to the left with rate 1. So it's what we are observing, it's a symmetric evolution. So from what we have seen yesterday, we expect that we'll need to rescale time by n squared in order to observe an evolution of the density. And this is our goal. So we would like to show that if I consider a function g, which is a test function, let's say a continuous function, defined on the torus, and if I observe my process at time t(n squared at site x, I average that over x. So I would like to prove that these converge to g x rho t x dx, so that for all t, there exists a density profile rho t such that this expression converges to that one, and where rho is the solution of some PD. So this is what we would like to do. And for that, let me introduce the empirical measure. So I will associate it to eta a measure in the torus. And how do I do that? So let me represent by M. This is the space of positive measures on the torus, which means on my interval 0, 1. And these are, they are positive. They will be represented by mu. And what I will require is that the total mass, it's bounded by 1. So the total mass, it's bounded by 1. So instead of writing this interval, let me write it as the one-dimensional torus by t. So the total mass is bounded by 1. And to eta, I want to associate an element of this space, so a measure, which I will represent by pi of eta. And how do I construct this measure? Well, to each particle, I consider that the particle has a mass which is equal to 1 over n. So if you give me a configuration, I will think that at each site which is occupied by a particle, I put a mass of size 1 of weight 1 over n. So pi of eta will be, well, I'll sum over all points in lambda n. I'll check if there is a particle at x, and if there is a particle at x, I will put a mass 1 over n at that site. So delta x is the Dirac measure at x, and 1 over n, I'm normalizing, so I will write this as 1 over n, the sum in x of eta x delta x. So if there is a particle at x, I just place a mass of weight 1 over n at this site. And so I will represent, so this is a measure. It's positive, and its total mass, it's bounded by 1. Okay? If I want to maximize the mass, I will place a particle at each side, and the total mass will be n divided by n, which is 1. Okay. And I will represent by pi g, if I take a continuous function g, and if I take a measure pi in m, I will represent by pi g the integral of g with respect to pi. So this is the integral of g with respect to pi on the torus, and in the case in which pi is equal to pi of eta, so this is the integral of g with respect to this measure, and this will be equal to, so I'm integrating g with respect to that. By linearity, it's the integral of g with respect to this delta x, which is g of x, and therefore that will be equal to 1 over n x gx eta x. So this is the integral. Fine. And okay. So let me consider quickly this space M. So I want to introduce a topology in M, and the natural topology is the weak topology. So I'll say that a sequence mu n converges to mu weakly if the integral of any continuous function converge to mu. So this is the weak topology. I'll say that the sequence of measures will converge to mu if this is true for all continuous functions. So my first claim is that this topology, it's metrizable, which means that I can define a distance which is compatible with this topology. So if I take two elements, mu and nu, in this space M, so these are measures positive and bounded by 1, I will define the distance between mu and nu in the following way. Let me take a family Fk of elements, so continuous functions, and let's assume that this family is dense for the L infinity norm. So you can construct a sequence of functions which approximate any continuous function in the L infinity norm. So consider such a sequence. It's easy to construct. And given that sequence, to make things simpler, I will assume that the function f1, it's just the constant function equal to 1. And let me define the distance between mu and nu as a sum for k larger or equal than 1 over 2k. And then here I take the difference between the integral of mu and fk and nu and fk divided by 1 plus the same thing. Okay. So I leave it to you to check that D is a distance. So please check that D is a distance. Construct also you have never seen a family of dense functions in L infinity, in this space. And then what I claim is that a sequence mu n converge to mu weakly if and only if the distance of mu n to mu converge to 0. Okay, so let me just check that. So let's assume that mu n converge to mu weakly. Okay, you want to show that the distance converges to 0. So what you do is you fix an epsilon positive. Then once this epsilon has been fixed, you look at this distance and you see that these ratios are bounded by 1. So choose a k sufficiently large for this sum to be bounded by epsilon. So there exists a k naught such that the sum for k larger than k naught of 1 over 2k, that this is bounded by epsilon. Right? And now write the distance between mu and mu n as, well, it's bounded by the sum from 1 up to k naught of 1 over 2k, and I don't write again what's written over there, and then plus the sum for k larger than k naught, but the sum for k larger than k naught, from the definition, this is bounded by 1, so this is bounded by this sum, and this sum is bounded by epsilon. Okay. Now, I know that mu n is converging to mu weakly, which means that the integral of any continuous function g is converging to the integral of g with respect to mu, right? So this means that this ratio, this difference is converging to 0 for each fixed k. Okay? So you can find, you take k equal to 1. Since mu it's converging to, mu n is converging to mu weakly, you can find n sufficiently large for this mu n fk minus mu fk to be smaller than your epsilon. And so this will be bounded. Okay, so there exists an n1 such that if n is larger than n1, then this difference, mu n f1 minus mu f1, that this is bounded by epsilon for all. And you do that for n1 up to nk. You take the maximum. So for n larger than the maximum, what you know is that these differences are bounded by epsilon for all j between 1 and k naught. Okay? And so since this is always bounded by epsilon, this means that this ratio is also bounded by epsilon. And this means that this expression here will be bounded by epsilon times 1 over k, provided n is larger than this maximum between n1 up to nk0. Okay? And this gives you that this distance is bounded by epsilon, provided n is sufficiently large. Okay? So this proves that, indeed, if mu n converges to mu weakly, then the distance converges to 0. Now assume that the distance converges to 0, and so let's prove the converge. So assume that the distance mu n mu, that this is converging to 0. Well, you know that this means that mu n fk minus mu fk 1 plus the difference. So if I divide that by 2k, this is one term in the sum, so it's bounded by the distance. So this is less or equal than 2k times the distance between mu and mu n. And since the distance is converging to 0, this means that this ratio is converging to 0, which means that mu n fk it's converging to mu fk. Okay, and that you know, therefore you proved that for all k you have that mu n fk converge to mu fk. Okay? But this is not exactly what we need, because we need to prove that this is true for any continuous function. But now you fix the continuous function g, and you want to compare mu n g with mu g. But you know that this sequence that you started from, this fk, it's dense in L infinity. So you fix an epsilon, and you find a k such that fk minus your function g in the L infinity norm, it's bounded by epsilon. Okay. So by triangle inequality, this is bounded by mu k mu n g minus fk plus mu n fk minus mu fk, and then plus mu fk minus g. Okay. So remember, this represents the integral of g minus fk with respect to mu n. But now I can bound this integral by the L infinity norm so I can always bound mu h, okay, which is the integral of h with respect to d mu. I can always bound that by the L infinity norm of h times mu of the torus. But M is the space of measures for which this is bounded by 1. Therefore, I can always bound this integral just by the L infinity norm of h. So if I go back here, I can bound this first term by the L infinity norm of g minus fk, but this is bounded by epsilon. So the first and the last terms are bounded by epsilon, which means that this difference is less or equal than 2 epsilon plus un fk minus mu fk. But this converges to 0 because I know that mu n fk converges to mu. So from the fact that this family is dense in L infinity and that mu have mass, total mass bounded by 1, we get that indeed this distance is equivalent to the weak topology. Okay, now, second fact which I claim is that this space is compact. So weakly compact, which means that if I consider a sequence mu n in mu, I can extract a converging subsequence. Okay, so I only sketch this proof. So I take mu n, a family in M, and I want to extract subsequence which converge. So what you do is you take your first function f1, and you know that this is bounded, right? Because this is bounded by the L infinity norm of f1. So we have a bounded sequence of real numbers, which means that you can extract converging subsequence. So this means that you can extract a subsequence for which mu and k f1 converge to a number which I will call alpha 1. And then you proceed to f2. So you extract a subsequence which converge. Then you use Cantor to get a subsequence for which you have convergence for all j. Now you want to define a measure which satisfies this identity. Okay. So you want to, you define this. So this is a functional. Or if you wish, so this is not maybe a good notation. So let me define a linear functional. So I'm defining t in this way. So t is defined for all fj. And I want to extend. So what I know is that t of fj, right? Well, t of fj is this limit, but this limit is bounded by fj, so this it's bounded by the L infinity norm of fj. Okay? This is by our construction. Okay, I know that mu n fj, it's always bounded by that, so any limit will satisfy this. Okay, alpha j has this property. So once, so t is defined in all these fj. It's linear. So t, if I take, let me extend it by saying that ta fj, it's equal to a tfj. And let me extend t to the space of continuous function by taking, so if you have a continuous function, you know that there is a sequence fk which converge to this function. So let me define t of this function as the limit. So you have to show that the limit exists, but this comes from the Cauchy property. And so now, once you extend this linear function to t, it still satisfies this bound. And it's linear. Then you at this point, you use Rie's representation lemma, which tells you that, well, then there exists a measure such that t can be written as mu of f. And now finally, since you know that this is alpha j, it's t of fj, you have that this mu n fj is converging. For this sequence, fj is converging to alpha j, which is mu of fj, and that will tell you that mu and k converge to mu weakly. Should I give you more details, or it was too fast, or are you fine?
The functional t will depend on the subsequence chosen, right?
Yeah. Yeah. I went very fast because I don't want to spend too much time on that, but If you have no questions, I will just go on. Otherwise, we can discuss more of these. Okay, so what we proved is that mu m, it's weakly compact. And what I leave it to you as an exercise to show that m is separable. So you have to construct countable dense family of measures. Right, so, okay. Now, I have my exclusion, my symmetric exclusion process, eta t. And from this, I can define this empirical measure of eta t. Okay. So for fixed n, there is a one-to-one correspondence between etas and these measures. Okay. If I give you a configuration, you can construct the measures just putting these mass 1 over n at each site where there is a particle. And if I give you a measure which places masses 1 over n at a certain number of points of lambda n, you can reconstruct the configuration. So there is a one-to-one relation between these measures, which are combinations of direct masses at points of lambda n, of direct mass of weight 1 over n, and my configurations. Which means that actually this is a Markov process, so a Markov chain, but instead of taking values in omega n, now this Markov chain, it's taking values on the space of measures m. And so I can understand this process as a process in an interval 0t, m. Okay, remember that if I had Markov process xt, taking values on some space E, I could construct a measure on this space where instead of M I have E, where this space, it's the space of right continuous functions with left limits. And if M is a complete separable metric space, I define the metric in this space, a topology in this space. So what we have is that if I give you an initial state, and since we define this Markov chain, with these two ingredients, now I can define a measure in this space. This is the measure induced by the initial measure of my process and by the dynamics. So let me represent by nu n. This is the initial measure of my process. So it's a eta belongs to omega n, which is 0, 1 to the power lambda n. And now nu, it's a measure over the configurations. So nu n is an element of, let me represent by P, the set of probability measures over my space omega n. Okay. So this is the initial distribution. It's how I distributed particles. And if you want to fix idea, let's say that I give you a function rho, which is continuous on the torus, and such that rho x, it takes only values between 0 and 1. Now I can take, for instance, to fix ideas, nu to be the product of Bernoulli measures with density rho. Okay, so let's start with this measure. So we place particles independently at each site. But the density, the probability that we put particles depend on the point where we are. So this is the initial state. And then we consider the evolution, our Markov process eta t, which is the exclusion process. Okay. So let me just put an n, superscript n, to say that this process evolves on this space omega n. So it depends on n. For each n, I have a process, a different process. And this corresponds to the evolution of pi of eta and t. So given this configuration, this evolution, I apply pi, and I get evolution of measures now. These are measures which are evolving in time. And I will call this object here pi n of t. So pi n of t, it's now a Markov, continuous time Markov chain. But instead of taking values in omega n, this process takes values in m. Okay, you start, let's say that you start with a configuration. So this configuration corresponds to a measure which puts mass on these 3 points, mass 1 over n. You let the process evolve. At a later time, these particles maybe are here, and then you have a new measure, a new pi n t. Okay? So it's an evolution. But now, the advantage between eta, pi over eta, is that the state space of eta was changing. For each n, it was omega n. This space was changing. Now pi n, for all n, they take value in the same space, which is the space of measures. And then I introduce this space D. And let me remind you of what I said. If I have a sequence of random variables xn, you have seen many different definitions of convergence. One definition of convergence was the weak convergence. So you wanted to prove that a sequence xn converge weakly to x, which means that if you take the expectations, so if you take any bounded continuous function f, that this was converging to the expectation of fx. So for all function which is continuous and bounded. But in order to study or to prove these weak convergence, what you did is, well, these random variables might be defined in different spaces. Okay. So let's say that xn is defined in some space omega f and p. And what you did is to project this variable on R. So you consider a measure mu n, which is the measure on the space R with the Borel sigma algebra induced by xn and this space and this probability p. Right? So you define mu n as this probability p composed with xn minus 1. And you reduce the study of this weak convergence to the study of the weak convergence of mu n to mu. Okay? And how you prove this type of results? Well, by proving first, so the typical method in which you prove this result, it's by showing first that this sequence mu n is compact, which is tight. So there is a compact which contains everything, and then you show that if you characterize the limits of the converging subsequence. Right? So we proceed in 2 steps. Prove tightness first, and then prove uniqueness of limit points. Right? And so, well, this is in the context of random variables. In the context of process, you do exactly the same thing, but now xn, it's not an element of R, but it's a process. But this process, it's continuous, it's right continuous and has left limits. So the space on which you will work is this space of right continuous trajectories with left limits. All right, so now I have pi nt, which is a process. Okay. It's a Markov chain, taking values in the space of measures. Say that this Markov chain is defined in some omega pf. So now with pi n, I can construct a measure in the space d0 infinity m, which is endowed with the Borel sigma field of this space. Okay, we have seen that this space is a metric space, and therefore, once you have a topology, you have open sets, you can now define the smallest sigma algebra which contains the open sets. This is the Borel sigma field. So the Borel sigma field of this space is well defined. And therefore, this process and this measure P will define a measure here in this space, okay? Which I will represent by P n, because it depends on n. And just to remind what is the initial measure, the initial distribution, I will add a subscript by saying that, well, we started from this measure. We started from the initial distribution of eta. It's given by nu n. Okay, so in the case in which nu, or maybe I'll put a second bar, so in the case in which nu, it's the product of Bernoullis, that will be this measure. Okay? So this is a measure in this space. And now, all my problem will be to prove that this sequence of measures converge to a measure. So this is the goal. And again, so how you do that? Well, you follow the same strategy. You have to prove compactness, tightness, and I have provide some results which yield tightness, and then we have to characterize the limit points. Okay? So tightness, remember I mentioned the Aldous criterion, and uniqueness, well, you have to, on each case, you have to prove uniqueness. So this is model dependent. But tightness, you have a strategy to prove it. So what I'm proposing to do is to prove this result in the case of the symmetric exclusion process, where say that you're starting with a product of Bernoulli measures. Okay. So there are two results we need to prove: tightness, uniqueness. So I'll start with uniqueness. Which means that I'm assuming that pi n new n row point, I'm assuming that this is converged to some pi. And I want to show that, well, then pi has to be something. And in order to prove that, I will need to introduce martingales. Okay. So have you seen martingales before? Do you know what I'm talking about? You all know? Do you know? No, you don't know. So let me tell you in 5 minutes what a martingale is. So martingales. So I have a probability space. And in this probability space, we have a filtration, which is something we have already seen. So this is a sequence of sigma fields, which is increasing. So Fs, it's contained in Ft. If S, it's less or equal to T. And they are all contained in this big sigma algebra F. Okay, so this is my starting point. And then I have a family, a process, xt. And I will say that xt is a martingale if the following holds. So xt, it's a martingale. So the first assumption is that, well, this family, it's adapted to the filtration Ft. So this means that xt, it's Ft measurable. And remember, I'm representing that by this symbol, saying that xt belongs to Ft, to say that xt, it's Ft measurable for all t. So this is my first requirement. Then my second requirement is that they are integrable, which means that the expectation of the absolute value of xt is bounded for all t. And finally, I will require that if I take xt and I take its conditional expectation with respect to fs, for s smaller than t, then this is xs. Okay, so in some sense, it's a fair game. If you have a certain amount at xs, so the average amount at time t, given everything which happened up to time s, it's the amount you have at time s. So it's a fair game. Okay. So this is the definition of the martingale. And okay, what's very nice about martingales is that they appear everywhere. That one very, okay, so that you have very good limiting properties, sorry. So If you have enough integrability, then you can prove that xt will converge. If xt is a martingale which has nice integrability property, then you can prove that xt converge. So this is one reason to study martingales. But the reason that we will study here is that if you have a sequence of martingales, x and t, and that if you know that this converge to some process xt, and you have well, integrability properties, then xt is a martingale. Okay, and that's very nice, because this is not true for Markov chains. Okay, so if you have a sequence of Markov chains, it's not clear that the limit will be a Markov. But the martingale property is conserved in the limit. And here, we are very much interested in the limits. So this is a reason for these martingales to be popular. So now we are working in the space of continuous time Markov chains. So xt, let's say that xt is a Markov chain. Let me represent its generator by L. Well, what I claim is that this Markov chain is evolving in a finite state space E. So what I claim, so proposition, is that if you take any function f from E to R, then fxt minus the integral from 0 to t of L f xs, that this is a martingale. Okay, so let me prove this first result. So let's go back to the definition. Here, what is the filtration I'm working? Well, the filtration, ft, will be just the sigma algebra generated by xs for s less or equal than t. So it's clear that this variable is ft measurable. Since we are working in a finite state space, f is bounded, so it's clear that this object is also bounded and therefore integrable. So what really remains to prove is that the expectation, so since I'll prove that this is a martingale, let me call that mt. What we need to show is that the expectation of mt given fs, that this is equal to ms. So let's prove that. By definition, mt is fxt minus the integral from 0 to t of L f xr dr, and this is given fs. So let me use linearity. So this is the expectation of f of xt given fs minus the conditional expectation of the second piece. But the second piece, I will divide this integral as an integral from 0 to s and the integral from s to t. From 0 to s, I have only times r, which are smaller than s, and therefore these variables are all fs measurable. So the conditional expectation is equal to itself. So there is a first piece which is the 0s of L f xr dr. And then there is a second piece, which is what happens after. But what happens after? Let me exchange the integral with the expectation. Right, so I just exchange the integral from S to T with the expectation by Fubini. Everything here, it's finite. Okay, so now we can recall that the process is a Markov chain, and therefore that the process is a Markov chain, and therefore that this conditional expectation is actually equal, so by the Markov property, this is actually equal to, well, the expectation starting from xs of f xt minus s. Right? This is just the Markov property. Then there is a second term, which I don't touch. And there is this third term, which I will again use that the Markov property. So this is xs, now lf at xr minus s. All right? And what I want to show is that I want to prove that this conditional expectation is MS. Okay? So here, if you see the definition of MS, I have here a piece of M, which corresponds to this one. So what I need to do is to show that the first minus the third one, it's equal to fx. Okay? Because if I prove that this difference is fx, what will remain? It's fx minus this integral, and this is exactly ms. So this is what I have to do. I have to show that this difference is equal to fx. Okay, so this is the goal. Fine. So what is this? This is, let me represent by P the semigroup. So this is the semigroup at time t minus s applied to the function f and computed at xs. Okay, so this is the first one. And then the second one, which is minus. Okay. So here, maybe let me call this R prime. So R prime, it's R minus S. So R prime, it's going from 0 to t minus s. So this is 0 t minus s. And then, since this is R prime, what I have is that this is P R, which is R prime, applied to the function LF and computed at xs. Okay? And I want to show that this is equal to fx. So let me call that point x. And what I want to show is that this is equal to fx. Okay? For all t minus s. So if I call that t prime and that t prime, so what I need to show is that pt f x, it's equal minus the integral from 0 to t of PR LF at x dr, that this is equal to fx. And this for all x and all t. Okay? This is what we need to prove. So what I see is that at time for t equal to 0, this is okay, because for t equal to 0, I don't have the second term, and pt at time 0, it's the identity, so this is fx, and this is indeed fx. Okay? So this identity holds at time 0, and if now I take the derivative of this expression, well, if I take the derivative in t of this expression, what I get is that, remember, ddt of pt, we proved that it's either lpt and it's also ptl. Okay, we proved that. So this is what we call the Chapman-Kolmogorov equations that we proved. So if I take the time derivative of pt, I will get that the first term, it's pt, let me write it as ptl, or no, let me write it, yeah, ptl of f at x. So this is the derivative of the first term, and if I take the derivative in t of the second term, what I get, it's also ptlf. So the derivative of this expression in time, it's equal to 0. So since it's equal to 0, this expression is equal to fx at time 0, it's constant equal to fx, and we proved indeed that this identity holds, and therefore that M, it's a martingale. All right? So this is a martingale. Now, sometimes we will need functions which depends on time. So I leave it to you as an exercise, but the proof it's exactly the same, to show that if I take a function which depends on time and space, ft, xt, then what I get is that this minus 0t ds plus L applied to f s xs ds, it's a martingale. Okay, so what you have to understand here is that you have dsf computed at sxs plus lf computed at sxs. Where here you consider s as fixed, so you have a function of the position, and you're computing L of f. Okay. So time is fixed, it's a function of position, and you're computing the generator applied to this function. And what I say is that with the same proof, you can show that this is a martingale.
In the differential operator, it says that it's in the first coordinate. The LS.
This one? Okay, so this one, it's you're taking this function f, and you're taking the derivative with respect to the first coordinate. And while this one, you fix the first coordinate, you think it's a function of the second, and you apply the generator. Okay? Okay, so these are, it's an exercise. I leave it to you to an exercise just to check if you understood the proof. And then what I will need, it's a second result. that I will use. Now, you know that this is a martingale. So let me take the square of this martingale, and let me represent this martingale. It depends for each function f. I have a different martingale. So let me represent this martingale by mft. So you fix a function f. You have your martingale mft. You take the square of this martingale. And what I claim is that this minus the integral from 0 to t of L f square. So you take your function f, compute f square. Now you apply L to f square minus 2 fxs Lf xs, that this is a martingale. All right? So let's prove that. In order to prove that, well, I have mf, it's given by this formula. Let's expand this square. So when I expand this square, so I will just consider the first term, and I want to produce martingales. So if I consider the first term, it's the square of this difference. So if I take the square of this difference, what I get is f squared xt minus 2 times f xt, the integral of 0 to t L f xs ds, then plus the square of the So this is the first term. Now, if here, I know that if I subtract and add L applied to f squared at xs, f squared xt minus this integral is a martingale. So this is what I do. I add and subtract this martingale. By subtracting, I get a martingale, and the plus will give me a term which will cancel this one. Okay? So this term has been cancelled. If I say that the first term, so the first term, it's equal to a martingale. So the martingale, it's f squared minus the integral of L f squared. And then I have the plus, but the plus has cancelled with this one. And so this is a martingale minus these two terms. Okay? So up to now, I just expressed d squared as these two terms plus a martingale plus a term which cancels with this one. Fine. So now I want also to make appear a martingale here. So what I will do is I will add and subtract L f xs ds. So by subtracting, I get a martingale. By adding, well, I get a term. So let me write this as minus 2. So first, I get the minus sign. With the minus sign, this is the martingale mft, and which is multiplying the integral 0t of L f xs ds. Okay, so this is one term. And then I have the plus. So I have the plus with this one, but I have a minus 2 here. So these terms are equal, minus 2 of the square, but I have a plus the square, so I get a minus . Okay, so these are. So up to now, I proved that the first term is equal to that plus this term. Okay? Fine. Now, I want to take this term and write xt, yt as the integral from 0 to t of xs dys plus 0 to t ys dxs. Okay, well, you can justify this identity and plus a constant, which is the one you get at time 0, but say I will apply to this to a term which is 0 at 0, so that will never appear. But okay, so you can justify this identity just by realizing that all these objects, they are constant on intervals. So you can decompose your process along. So these have to be understood. So this process, they have jump. So these are integrals in the still sense. Okay? And you can justify this equation just by, in our example, just by recalling that these functions are continuous on intervals. So you just decompose your path over all jumps, and then you compute what are the contributions of each of these jumps to get that you. Okay, because, well, this will give you that x, this integral will be actually a sum of xtj times the difference of tj minus tj minus. And tj minus corresponds to tj minus 1, because the path is constant on the intervals. Okay? So what I'm saying is that x and y are constant on intervals. So you can define tj's, the points of the jumps. Since y is constant, this means that this integral is actually Dirac measures at the jumps. So that integral will be actually a sum of xtj times the jump. But since it's constant in interval, the value tj before the jump corresponds to the value of the previous jump, at the previous jump. So this will be ytj minus 1. Okay, because in the interval tj minus 1 up to tj, the path is constant. Here it may be a jump. So the value at the left, it corresponds to the value of this, and this will get you a telescopic sum to get that these two integrals will give you the difference between xt, yt minus x0, y0. Okay? So check what I'm saying, and let me use this identity. So so I will apply this identity to this term, and then I will use the following fact, which I won't prove, is that if you have a process Zs, which I'm integrating with respect to a martingale, this is a martingale. So you'll learn that when you will learn Ito integration theory. So whenever you integrate something with respect to a martingale, what you get is a new martingale. So by using these two properties, these two facts, I will write this term, which is mt, so mtf times this integral from 0 to t lf xr dr. So this will be my, say in this formula, my x. This will be my y. So this, the first term, I'm integrating it with respect to y. So this is the integral from 0 to t msf dy, but dy it's just L of fx ds. Okay, d of this object will be simply this object. So this is the first term. Then I'll have the other one, which is the integral of this with respect to m, but this is a martingale. So let me call that the second martingale. And then I have this term, but as I told you, y, my process y at time 0 is 0, so there is no such a term. Okay. And now recall what is m. mf, I gave you the formula over there. So this is f of xs, which is multiplying by lf of xs ds. So this is one term plus or minus and then I have an integral from 0 to s of lf xr dr times lf xs ds. Okay. So, and plus a martingale. So now let's recall what we are doing. We are computing this term. There is a minus 2 in front. So this minus 2 will give me a minus 2. Okay, minus 2 here, plus 2 here, and a minus 2 here. So this is still a martingale. That's fine. Then you see here what appeared, it's the minus 2 FLF, which is this term. Okay? So that term here, when I'm computing this term with the minus 2 in front, what I obtained, it's exactly this term. So this term here will cancel with that one, which means that up to now, what if I call this my equation star? I proved that star it's equal. First we have the martingales. So there is the MT1 minus 2 MT2. So this is a martingale, which I will call MT3. So this is M1 minus 2 M2. Okay, so if you take a martingale, multiply by a constant, it's still a martingale. So these are martingales. Then this term cancels, so all terms here have cancelled. And what remains is that I have this term and I have this term. Okay? So let's write this is equal to a martingale plus so 2 times the integral from 0 to t, the integral from 0 to s, then okay, so this is this term which we obtained. So when computing that, we obtain these 3 terms. One cancelled, this one is a martingale, and this one I just wrote. And I have this term. Okay? So minus, and this term appears with minus t. Okay, so this is what we have. And what I claim is that this term is equal to that one, because, well, if you take the derivative of this term, you get 2, and you get then the integral of that. Or if you wish, if I just use this formula again for the square, okay, for this term, now x and y are equal. X and y are equal, so this gives me the integral of x with respect to dy 2 times. So it's 2 times, so let me write it. This is 2 times minus 2 times the integral 0t of one of them, which is 0L f xr dr. Now, d times this term, but when I take d, I get L. Okay, so this term, it's equal to that one by that formula, and therefore they cancel with this one. So indeed, star is equal to a martingale. This proves that this expression is a martingale. Okay. And this is what I will need in order to prove uniqueness. Okay. And again, I could have added, the same proof will tell me that these objects are martingale if I consider functions which depends on time. So second exercise, do the same computation, but now with functions which depends on time. Okay. So this is my claim. So this is my claim, and now I can use this in order to so I'll take a function g which is, let's say, smooth. So let's say that it's of class C2, twice differentiable, defined on the torus. And I will consider pi n t of g as my function. So that will be my function f of eta t. Okay. So remember, this is the integral of g with respect to pi nt. So this is equal to 1 over n, sum over x in lambda n, gx eta x at time t. So the martingale I want to construct, it's the martingale associated to this function. This is a function of the configuration. Give me a configuration. Here's the value of this function. Now, we have seen that if I have a Markov chain xt, I take a function of xt, then I can construct a martingale. The martingale will be given by f of eta t minus the integral from 0 to t of L of f of eta s ds. So we have just seen that this is a martingale. So what I need to do is to compute this term for this function, f. Okay? So let's do that. So L of a function f computed at the configuration eta, remember, is the sum for all x in lambda n of f in which I exchange x and x plus e of eta minus f of eta. Right? This is the generator of the exclusion. So I just replace f by that function. So I have a sum of x in lambda n. Now, f is this function, and I'm computing this function at sigma x, x plus e of eta. Okay? So let me replace this x by y. So it's 1 over n, a sum over y of gy. But now I'm computing not at eta, but at sigma x, x plus e of eta. Sigma x, x plus e of eta. And this is computed at y. So this is f of sigma xx plus e eta, then minus f of eta minus 1 over n, sum over y, g of y, eta of y. Okay? So this is L of f. And what do we know about this difference of this new configuration? Well, this new configuration coincides with eta everywhere but at the site sig x and x plus e. Okay? So this is equal to eta y, and if y, it's different from x and x plus e. Okay? Which means that this difference will be 0 unless y it's equal to x or x plus e. So I'll take out the 1 over n. I have a sum for x in lambda n. And now this sum, it's reduced to two terms, y equal to x and y equal to x plus e. So let's see y equal to x. At y equal to x, I have g of x, because y is equal to x. And if y is equal to x, this term I exchange what happens at x and x plus e. So I'm computing this configuration at site x, which means that this is equal, so sigma x plus e eta at site x, this is eta at site x plus e, because I exchanged. So this term gives me eta x plus e, while this one, well, it's just x. So this is, I have here y equal to x, eta x plus e, and this one, it's eta x, but I have a minus sign, so it's minus eta x. Okay, so this is the term y equal to x. And then I have the term y equal to x plus e. If y is equal to x plus e, well, I have to compute this object. This is sigma x plus e eta at x plus e. Since I exchange the value at x plus e, it's the value of eta at site x. Okay? So this term gives me a contribution eta x, while this one, y is equal to x plus e, it's minus eta x plus e. Okay? So, in conclusion, is that this is equal to 1 over n, the sum over x. And let me write that as eta x plus e minus eta x. And then I have gx minus gx plus e. So let me put minus maybe gx plus e minus gx. Okay, so this is L of f. And now what I want to do is I want to integrate that by parts. So this one, I will call that x prime. X plus e will be x prime. So since I'm doing a sum over the torus, when you just translate by 1, you don't do anything. So you're still summing over all x. So this becomes eta x. But this one, x plus e becomes x, and x becomes x minus e. And then I have the second term, but this one I don't change because I have eta x. So this gives me eta x with a minus sign, gx plus e minus gx. And remember that I have a minus sign here, so this is 1 over x, sum over x, eta x. So there is the minus sign, so what it get g of eta g x plus e plus g of x minus e minus 2 times g of x. And this, I will multiply that by n squared. I will divide that by n squared, so I get n cubed here. And this is what I will call the discrete Laplacian of g at x. So the discrete Laplacian at g at x is just n squared times gx plus e plus gx minus e minus 2 times gx. And by doing that, you see that we computed so what we proved is that L of pi n g, okay, our function f was pi n g, that this is equal what appeared here, it's the integral of this new function with respect to the empirical measure, with a 1 over n square in front. So 1 over n square, then pi n, the discrete Laplacian of g. We just proved this identity. Okay? Right. So this is, so I know that pi n t g minus this integral from 0 to t 1 over n square pi n s g, discrete Laplacian of g, so that this is a martingale. And let me call this martingale M, the martingale associated to the test function g, which I'm assuming it's C2, and I assume that it's C2 because here I will have the Laplacian, the discrete Laplacian. Fine, so this is a first computation. Now what I claim is that this martingale is very small. So if I take the L2 norm of this martingale, it converges to 0. So remember that if I consider function f, I can take its, this is a martingale, so it's f x t minus the integral of 0 to t L f xs ds. So this was a martingale. And now I proved that mt f square minus an expression okay, I don't want to write, so let me call that gamma SDS. So this is the expression we obtained, so that this is also a martingale. If this is a martingale, I know that the martingales have constant expectation, right? If you have a martingale, you know that the expectation at time t, it's equal to the expectation at time 0. So what we know, since this is a martingale, is that the expectation of mt f square minus this integral from 0 to t gamma s ds, that this is equal to the expectation of this martingale at time 0, but this expectation of this martingale at time 0, it's m0 f square. Okay? And so this tells me that the expectation of this martingale, mt f square, it's equal to the integral of gamma s ds plus this martingale, but if you look here, this martingale at time 0, it's the expectation of f x0 square. All right? So since this is a martingale, I have an easy way to estimate the expectation of this martingale, the square of this martingale. It will be given by the sum of these two terms. So if I want to show that that martingale is small, what I have to compute is this term. So let me compute this term. So let me take a function f of eta, which in our case was the integral of g with respect to the empirical measure. And remember that gamma, the expression I wrote here, it's L of f squared minus 2 times f LF. Okay, this is what we proved. What I want to do is to get a simpler formula for gamma in the case of the exclusion process. So what is the generator? The generator, as we have seen, is a sum. So I'm computing L applied to f squared. So this is f squared at sigma x plus e of eta minus f squared of eta. Okay? So this is the first term. And then we have minus 2 f of eta, the sum in x of, because here appears LF, and here it's f of sigma x plus e eta minus f of eta. Okay. And what I claim is that this is equal. So take in the square minus f of eta and plus f of eta. Okay. So when you compute the square, what you get is first the difference, the square of the difference. Okay, keep it. Then you get plus f squared, but this will cancel with this one. And then plus 2 times f times this difference, but this is exactly that. So what I claim is that this sum is actually equal to the sum of the square of the difference. Okay? Well, so compute this square, so you get f squared, which is this term. Then you have plus f squared, but you have here plus 2 minus 1, so indeed you get plus 1. And then you have minus 2, the product, and this is minus 2 f sigma. Okay? So they are equal. Okay. So simple computation. And so what I want to compute, I want to use this formula in order to estimate the square of the martingale. So I have to compute gamma, and I just obtained a simple formula for gamma. So let's gamma, in the case in which f is equal to pi g, gamma will be equal to the sum in x. So 1 over n. So let me just recall y, gy sigma x plus e eta at y minus 1 over n sum in y gy eta y. And this we already computed, and well, okay, and there is a square. But we already computed this difference, just computed that, and what we obtained is that this is equal to gx plus e minus gx times eta x plus e minus eta x. And there is a square. Okay? And so, and there is a 1 over n, which I'm forgetting, so there is a 1 over n square. So let me put it here. Okay, but now you realize that what is the order of this sum? G is smooth, so this is of order 1 over n. I have a square, so 1 over n square. 1 over n square, so 1 over n fourth, and the sum 1 over n third. So this is of the order of 1 of n third. Okay. While this term here, it's of the order 1 over n square. Okay. And so let me write this as 1 over n square, the sum of gx x plus e minus gx square times, so this is a function. Okay, so let me write it. So if I call this function, if I call the function h of eta the function eta e minus eta 0 square, this is just a translation of this function. Okay? So let me represent by tau x of eta a configuration which is translated by x. So this configuration at y is the configuration at x plus y. Okay, so tau x is just the group of translations. And so if I call this function h, this function here is just you take the function and you translate it. And how you define the translation of a function? Well, it's computed at configuration eta is just h computed at the translation of eta. Okay? So this is just the translation. And, well, we defined here the Laplacian. So let me define the gradient. So this is n times the gradient of a function g computed at x. Okay, so the gradient will be this difference multiplied by n. So this is, sorry, it's 1 over n. So that this is order 1. It's the difference multiplied by n. Yeah?
The gradient is by definition the square of it?
No, it's the difference. And so we have here the square. And therefore, after all these simplifications, what I get is, as I told you, there is a 1 over n which gets out with a square. So I get 1 over n fourth. Then the summation in x of the gradient, discrete gradient of g computed x square, and then the translation of this function h. So this is gamma. Okay? And so maybe we stop here. So I computed everything that I need in order to show you that we have uniqueness of limit points. Okay, so we continue and we conclude on Tuesday.